Hello, this is Professor Todd Elliott once again, and today's video is on the 74 LS, which stands for Low Power Schottky, family of logic gates and ICs. Okay, just some definitions, and I'll show you where we pull these from. These are from the data sheet, which I have a little bit later in the presentation. So I'll show you exactly where I get them from. But this is for the 74 LS series. There's other series. There's high speed CMOS and ALS. There's a bunch of them. Anyway, to ensure that things work properly, they've been designed with specific input output voltage ratings, current ratings, to make sure that everything within the family, when you're hooking gates and counters and latches and whatever, just lots of different components together, that they're all going to work as intended. So with if you switch to another series, then the terms will be the same, but the values will be somewhat different. Okay, so anyway, but the concepts are the same, because we use the LS series in this course, in your lab kit. This is we're just going to stick with the LS series, but anyway, VOH is the minimum high logic gate output. Okay, that's at 2.7 volts. That's like the output of a gate. It's guaranteed by the manufacturer to be at least 2.7 volts. And of course, it can wander up to the power supply, which is typically 5 volts. VOL is the maximum low logic gate output voltage. That's worst case is 0.5, and of course the ideal will be 0. Okay, that's because of the transistor saturation voltage. We've looked at that in electronics. You now understand that you cannot make VCE stat equal to 0. Okay, so this is the upper limit. VIH, minimum high input logic gate voltage. That's on the receiving gate. This is the minimum. It needs to see a minimum of a logic 2 volts to interpret that correctly as a logic high. A little bit later, I have a nice graph chart that illustrates all this. So you'll see how it all works out. But just to define things now, that's what we're going to do. VIL, it's a maximum input low logic input voltage. Now, it's not stated maximum or minimum on the data sheet. It's just understood that that's what it means. It'll just say low logic gate input. But anyway, so that's the highest or the maximum logic level for an input or receiving gate, 0.8 volts. If it's more than that, it will not be interpreted as a logic low. IOH is the maximum high logic gate output current. It's minus 0.4 milliamps, sorry, which is 400 microamps. The minus simply indicates, and this is by standard accepted convention, that current flowing out of a gate terminal is current sourcing. It's considered to be negative, and current flowing in is considered to be positive, and that's called current sinking. IOL, maximum low logic gate output current, 8 milliamps. Maximum high logic gate input current, 20 microamps. That's how much each gate input will draw under a high state. And IIL, maximum low logic gate input current, minus 0.36 milliamps, which is the current required by a logic gate input under logic low conditions. Now, if you recall back to experiment 2, we used an LED, this is for the first time, in a current sinking arrangement. And the reason is the LED itself requires more than the 0.4 milliamps in order to turn it on, which is why you cannot drive with an LS series an LED directly the anode terminal. It must be the cathode terminal, so it's current sinking. Of course, and you can always go through a BJT transistor switch, which actually I've saved for the end. But as far as the gate limitations go, that's why it must be current sinking, which can handle 8 milliamps, which is adequate enough to illuminate the LED for us. Sorry. Okay, continuing here. VCC, the supply voltage. Again, this is from the data sheet. The manufacturer states that you, the user, must guarantee that the DC supply voltage must be obviously, filtered and regulated, cannot be less than 4.75 and shall not exceed 5.25. So that's the user's job, your job, if you're designing the circuit, to make sure that the power supply voltage always falls within that range. Fan out is a term used to describe the number of inputs that a single logic gate can drive. You can drive one output, say from an OR gate, can drive more than one gate inputs. You can connect them in parallel. Okay, for the LS series, that limit is 20 gates, which is quite high actually. Okay, duty cycle is relationship between the logic 1, the high portion of the signal, compared to the low, expressed as a percent. So I'm just going to do a little bit of a sketch here. Okay, all right. So if you had a logic pulse that looked like this, okay, right. So this is the high time, and this is the low time. The duty cycle is, and this is one cycle, is the percentage of the high time compared to the cycle. And the way I've drawn it there, it's equal high and low times. It's equal to 100%, but doesn't necessarily have to be that way. Okay, so anyway, and again, LSTTL stands for low power Schottky transistor. This uses the Schottky technology, which means that instead of a p-n junction, it's just the n. The p side is simply a metal, so there's no minority carriers, and it allows for much faster switching, which is desirable for logic gates to turn it on and off as possible. So that's based on the Schottky transistor. You're welcome to look that up and read about it, but it's not a new technology by any stretch. Okay, noise margins. Noise margins is basically the buffer, the wiggle room the manufacturer has built in between the input and output voltage levels to make sure that there's a little safety factor and it always works. Again, I'll show this when I get to the graphic. Okay, so anyway, that's the exact formulas. The high noise margin. This is called the low noise margin, and that's okay. All right, so this here is the is the noise margin graph, and you can see then the bit on the left, right? This is for like the driving gate. Now it doesn't matter what logic gate I use. Okay, so and there's more than just logic gates within the family. There's counters, there's shift registers, there's adder circuits, yada yada yada. Okay, they all designed to work together within the same family. If you need to mix families, there's interface ways to go from and to as needed. But anyway, that's not important for us right now. Okay, so just arbitrarily, okay, we're going to just represent like that. Okay, so going on the voltages that we just looked at, VOH, okay, is 2.7 volts. Okay, and of course it can wander up to the 5-volt power supply for the output. That's the gate output for logic 1. Okay, For logic low, this can range from obviously from 0 to 0.5 volts. Okay, that's because of the internal transistors. VIH. Okay, this is 2 volts. Okay, so notice that the output, the manufacturer says that the output gate will have a worst case logic high output voltage of 2.7, but then on the receiving side, it says we'll actually take it down to 2 volts. That difference right here is okay, and likewise VIL, right, is 0.8. So the manufacturer is saying, worst case, my gate will put out 0.5 volts, right? And these, and all manufacturers, of the LS series or the HCC, whatever it is, they have to adhere to the same specs. It's standardized across the whole family, regardless of who. It's not tied to the manufacturer. Okay. Anyway, but the input gate says I'll actually take a logic low up to 0.8 volts. Okay, so this is called this little difference here. That's like just the wiggle room safety factor, whatever you want to call it. So you have to make sure that your logic levels on the output side and on the input side don't fall in that indeterminate range, because if they do, then there's no guarantee that the system's going to work together. Okay, so the logic levels, whether it's an input or output, absolutely must, under all circumstances, stay within those specified ranges, and you never go in that indeterminate range, because if you do that, then there's no guarantee how the gate is going to react. You're on your own at that point. Okay, term current sourcing. Any of you that end up working in the field, you will very likely come across that when you're dealing with sensors and relay drivers and things. You'll run across the term syncing and sourcing. There's dedicated ICs for current sourcing, relay coil driver, things like that. That I remember working with years ago. But anyway, current sourcing, and I just modeled the output of the gate just by a resistor. It's a transistor, actually. And then the input, which is also a transistor input, by a resistor. But current sourcing, current flows out of the gate and then into the input of the load gate. Okay, so this is IIH. And this gate here is actually going to be drawing, under that conditions, 20 microamps, worst case. Okay. Current sourcing. Okay, and for some reason, just a couple little, not sure why my resistors are missing. Okay, these are the pull down resistors, and they're there to ensure that the logic gates, the level at the input is as expected. If you don't put those resistors there when you open the switch, all right, you will those inputs will be floating, and who knows how the gate is going to respond. You don't want to do that. So all inputs must have either pull up or pull down resistors at some point in order to provide consistent, expected, reliable voltage levels. Okay, this little note here. Okay, that should be an ohm. Anyway, so this is showing an AND gate. Could be any gate, doesn't make any difference. Okay, current output high, right? For 0.4 milliamps maximum, and that we saw that from the data sheet. This is why when you're using the LED, you either have to go current syncing, or or you have to use a transistor interface. Okay, go to a different logic family. They may have more current capacity, and you may be able to directly drive it. With the LS series, you cannot. Okay, so this is from a textbook we used to use. Okay, so this is showing. This is actually for the old TTL. TTL stands for transistor logic. Okay, it's still a good illustration. The LS, which I have a little bit down the ways here, is slightly different. But anyway, you can see then when the output is in a high state, that Q4, that upper transistor, right, is saturated. Current is going to flow like that, and then into the emitter of Q1. Okay, so this here is the source or the driving gate. This is the receiving driven gate, the load, whatever you want to call it. But you can see then that the current, right, when it's a high state, flows out of here and then into here. Okay, so current sinking. Current sinking is like pouring. You can think of it as current sourcing as you're pouring water out of a container. Current sinking is you're pouring water into a container. That's a silly little analogy I use to remember it. But again, modeling the gate internals as just resistors. Current sinking goes like this. Okay. Current input low. Okay, maximum. Okay, negative, and that's just because of the current direction flowing in. It's assumed to be negative. Okay. All right. So maximum low gate input current then is 0.36 milliamps, and actually you don't really even need that negative there. Just put 0.36. That's just good enough. Okay, right. Again, a little note about driving. That's not what I wanted to do, is it? No. Okay, that's why you can't directly drive an LED with the gate. What I mean by that is, okay, this is against the, okay, so this is not going to work because the LED is going to draw more current than is required. Okay. All right. So, okay, again, just using switches. Okay, these are still like the pull down resistors. Okay, current's going to be flowing like that, and then internal to the to the transistor. Okay, you can see then current's going to flow, forward bias there, right? This transistor has been turned on, right? It's going to flow, just sink, and then down to the ground. Okay. Okay, pull-up resistors. Again, it's application dependent. In this case, we have pull-up resistors so that when the switch is closed, right, then we have a direct path to the ground. So in that case, then that input is going to be 0, and this input, right, is going to be 0. If we then open the switch like that, okay, then we see a direct connection then from here then up to the 5 volts. So this is going to go to a logic 1. So either pull up or pull down resistors must be used. Again, depends on the application. Okay. Okay, so we're going to have a look at a data sheet. Again, it doesn't matter which one we look at. because they're all going to be the same as far as the voltage and current levels go. Propagation delays will vary depending on the particular device, because an IC with more transistors takes longer for a signal to work its way through. And we'll look at propagation delay in a bit, but the voltage and current levels are the same. Okay. All right. So you can see here. All right. I've highlighted everything in yellow. I thought was the most critical. Absolute maximum ratings. Okay, you're not supposed to use it at 7 volts, but the chip will not be damaged if you apply up to 7. The operating range, okay, is going to be in there, right? Okay, you can see where we get that from. Okay. Like there. Okay. Like that. And right, so those are the voltage and current specifications. Okay. The note about the propagation delays, which I haven't gotten to yet here, it just says more complicated devices, it'll take longer for the signal to propagate through. For this particular gate, you can see here then that it's not, okay, that it's not, that it takes some time from when the signal goes high to low or low to high to propagate through the through the gate. It's not instantaneous. Okay, so anyway, so let's continue on and look at propagation delay a little more officially. All right. Okay, TPHLH, low to high propagation delay time. Okay, so that's how long it takes for the signal to go from a low to a high. Okay, and TPHL, high to low propagation delay time, is how long it takes to go from a high to a low. Okay, so here we can see we have an input, okay, and this is starting to look more like, a real world logic pulse. We'll look at that in a little bit later. It's not usually a nice perfectly square. Okay, the output, right? Do you see right here? Okay, and do you see right here? Okay, so that is, those are those 2 points directly, and then for the non-inverting, then over here, okay, input goes like this, okay, then the output, right, TP from low to high, and then from high to low. Okay, so basically, it takes time, right? So you see how, like, this point here and this point there, if the gate were ideal, they would be vertically lined up, but they're not. They're shifted in time because of the propagation delay. And likewise, that point there and that point there are not lined up. It's shifted in time because of the propagation delay. And as you run pulse signals from one gate into another, the propagation delays, of course, accumulate. This is per gate. Okay, so it limits how fast you can clock or pulse a given circuit. Okay. All right. So this is another illustration. We have the logic input, like there, and then we have the output. Okay, The measurement points are typically by convention taken at the 50% points, okay, of that slope. That's sort of by convention. And you can see then, okay, right away then where these values fall, right? So this one is TPHL, TPHL. So this one has a maximum. It could be less. That's a worst case. Okay, so that there is 18 nanoseconds, and then TPLH to go from a low to a high. Again, worst case is 18 nanoseconds. Okay, right, and it gives you the minimum values. But worst case, that's the maximum. Okay, and that's always on the data. Rise and fall times is by convention from the 10% to 90% points, and if you're going high to low, from the 90% point to the 10%, right? If that's considered 100% of the pulse amplitude, okay. All right. So TR is the rise time, TF is the fall time, and you can easily measure that on the scope. Okay. Non-ideal signal. Okay, so signals are not in the real world nice and perfectly square. Okay, they're more distorted. Okay, and they can be distorted because of overshoot, where the signal goes above its baseline amplitude. Ringing, droop is where it falls a little bit below here. Okay. Then you can have undershoot, where it goes then below, right? So undershoot, it goes below and then oscillates a little bit. All this is caused by capacitance and inductance in the wiring primarily. Okay, and the higher the signal frequency, the more pronounced the effect. You can see then the rise time is taken from the 10 to 90%, the fall time from the 90 to the 10%, and then right in the middle here, the pulse width by convention is taken in 50%. Okay, so this is looking more like a real world pulse. They're not all just pretty and square. If only, eh? Okay, so overshoot and ringing, just a little bit of notes about that. Okay, overshoot is that little bit there. Okay, and undershoot is that little bit there. Okay, so it's going above and below the baseline, if you will. Okay, the ringing is just due to these oscillations, right? It just causes noise, right? All this is caused by stray, parasitic, unwanted resistance capacitance in the wiring. Okay, if you were to build the circuit when we were in, and I took this in school, I believe we built this. I think that's where I got it from. This sort of circuit with a pulse input will give you that level, that sort of output. Okay. All right. Okay. Rise and fall times. Okay. Again, it's due to stray capacitance, right? You have two wires in a conductor. There's capacitance between them. There can be inductance, right? All these things conspire to distort the signal. Okay, right? So again, the rise time is going from the 10% to the 90%, and the fall times from the 90% to the 10%. Okay. Okay, unused gates. It depends on what the function, the logic family is. Okay, but this is from the old TTL series, and it says TTL series input should not be left floating, but they should be tied somewhere. LSTTLs are a little bit different, right? It says do not connect an unused LS input to another input of the same gate, right? This method is recommended for normal TTL. So basically, if you have unused terminals, they can act as antennas and inject unwanted noise into the system. Okay, so as always, refer to the to the data sheet. Okay, it'll have notes on there. Manufacturers also produce application notes, which is probably where I got this on, right? Which may be a separate publication or included with the data sheet, right? That gives you more information. Okay, so anyway, for our purposes, you can just leave them floating. Real world, probably not. Oops. Okay, TTL inverter. Okay, again, this is from the old TTL series. This diode here was used. And we've got some, I'm not quite sure why. Got some missing lines here. These diodes here were used. That D2, sorry, the single diode was there to because this used the old TTL series. It was much slower switching. When the switching from the low to a high, it's possible for the upper transistor Q4 to just partially turn on before the lower transistor Q3 was fully turned off. In that case, there would be a moment, could be a moment where the power supply was, not direct, literally, but ineffectively kind of shorted, and you would get spikes on the power supply line, which had to be filtered out. Okay, so anyway, so that's a input of a TTL gate. Okay, I don't expect you to memorize this, though. Don't worry. TTL NAND gate, right? Okay, so this is a two input NAND. Okay, right? So those are the inputs. Do you see they're actually feeding into, right, a multiple emitter transistor? That's actually what the inputs are. These are protection diodes that protects against high negative voltages, and you see if a high negative pulse came along, the diodes would conduct and dump it to ground. Again, this D3 was there because the transistors could not turn it on and off quickly, and is to prevent what was called switching spikes on the power supply rail. The internal structure here changes based on what the logic function is. Okay. By the way, LSTTL. Okay, so this is the schematic symbol for a Schottky transistor. Notice the little S type symbol. There's no diode. There's no diode here because the transistors turn on and off quickly. So there's no danger of causing switching spikes. All right. Again, Schottky diodes. Okay, so all right. Again. Okay. VCE SAT. Oop, wrong transistor of this one here. Don't have to memorize that. LS TTL driving an LED transistor. Okay, so here we have a just an OR gate, pick any gate you like, driving an LED, which is in series with the current limiting resistor. Notice how we have set up here in a current sinking arrangement, because that's the only arrangement that provides enough current up to 8 milliamps to illuminate our LED. Okay, so over here, okay, you'll see that I've set, let's assume that the output low voltage, and what is that? Okay, that is just, okay, that is VE SAT of that lower. So that's what we know. That's actually not going to be zero, right? Okay, so if you look at this, right, you can easily calculate the value of resistor there, to give us the current that we want. I'm going to redraw that a little bigger on the next slide. If you just give me a sec, I have to turn my light on so I can actually see what I'm doing. So hang on a sec. Okay. All right, that should be a little bit better. Okay, so here is our game plan, and this is identical to the circuits we were doing in electronics. The only difference is, right, it's a logic gate, big deal, instead of a switch, right, and we have to deal with the output low voltage, right. So no big deal. It's everything's the same, right? All the same concepts and everything. There's no difference. Okay, so anyway, make sure you write this down before you go on and solve it. Okay, you can just pause the presentation. Okay, want to know what that is? Okay, so we're assuming that the LED voltage is 2.1 volts. Okay, and we want 7 milliamps of current, and the output low voltage here, we're going to assume it's 0.25. Okay, under those conditions, what's R? Well, voltage VR equals VCC minus the LED minus VOL. So that's 5 minus 2.65 volts. So therefore, by Ohm's law, R equals VR divided by I okay, 378 ohms. So you just go pick the nearest standard size, which is probably 380. So, okay, that's it. That's all there is to it. Okay, so let's try another one. Okay, I'm gonna redraw this a little bigger, but we want to work out what size base resistor do we need to satisfy all these specifications. Okay. All right. So anyway, let's go and do that. Sit on my slide here. This should have been just 5. All right, so this is very slightly 9.1. The transistor will easily handle that. That's because I put the 5.1s. Maybe I was thinking that. I made this up years ago, so I don't really remember. Anyway, I'm just going to correct that and just okay, this is going to be 10.9. Okay. Anyway, that corrects that. Okay, so we have, again, please make a copy of this. So we're going to assume that's 330 ohms. We're going to assume that the output high voltage is 4 volts. Okay, so it can range between 2.7 and 5. If you look back what we did earlier, 5 volts, right? So we have the transistor is buffering the gate output to the LED, so therefore we can turn on the LED when the output is high, which we couldn't do directly without that transistor. We want VCE SAT to be 0.3 volts, and we're assuming the LED voltage is 1.7 volts. Okay, that's what I want to find, right? So go ahead and VRC and write this down. And I'll just solve it on this. I just realized. Okay. And so I'm making a note here for myself. 5 volts. And this is 9.1. Okay. All right. We're going to go back on the next slide. Okay. All right. So therefore, then we can say then that when we apply a logic 1 at the output of the gate, it will forward bias the transistor through the current gain, then will illuminate the LED, right? So step 1, we can say then that the collector current is equal to VCC minus, V LED minus, okay, so those values were all given to us. All right. So this is going to be 5 volts minus 1.7 minus 0.3, 5.0 minus 1.7 minus 0.3, okay, equals 3 volts, and divide it by the 330 ohms, okay, equals, well, technically 9.1 milliamps. Okay, step 2. I'm just going, okay, change it just. Then we're going to say then, because the VCE SAT is equal, we want it to be equal to 0.3 volts. If you look back at the collector characteristic curve, okay, we are well under 0.7. So the transistor is working in the right now, and the lower that saturation voltage, the lower the gain is. So fully saturated, the gain, somewhere, 10 to 30, 10 to 40, somewhere in that for the beta. What step are we on? Something in that. Okay. All right. The saturated region. Okay. So we know the beta DC is going to be low. Okay, so because the transistor is saturated, let's just assume beta DC is 30. Therefore, the base current equals the collector current divided by the beta DC. So that was 9.1 divided by 30. So that's 9.1 divided by 30 equals 303 microamps. Okay, all right. But I would give you an assumed beta to use on the test. So this is just an example. Okay, we have 3 base resistor voltage VRB equals the output high voltage start at the logic gate minus VBE. Okay, so that equals 4 minus equals 3.3. So 1, okay, 4. Again, I'm assuming you're looking at the drawing at the same time. Therefore, RB equals VRB divided by IB. So that's going to be 3.3 volts divided by 303 microamps. 3.3 divided by 0.303 equals 10.89K, so 10 or 11K, something more. One more. Okay, so we're going to again assume that the beta DC is 30. Okay, same sort of arrangement here. We're going to assume our VCE fully saturated is 0.3. We're going to use a 10 volt power supply now, because now we have the transistor. We can switch it up to use a much higher voltage. Okay, we're going to do exactly the same sort of thing. RC is going to be 2K. The LED voltage is 1.7, right? So what does VRC equal? VRC equals VCC minus VLED minus VCE sat, right? So that's our VCC supply of 10 minus 1.7 for the LED minus VCE sat is 0.3. So that equals 8 volts even. Okay, 2K ohm resistor, right? You get your 4 milliamps of current. If you wanted more current, right, just lower the value of RC. Okay. And then again, our goal was to calculate what is RB, right? So then we can simply say then that IB equals IC divided by the beta DC. So that's the 4 milliamps divided by the 30. That's 133 microamps, right? We have 4 volts here. We have 0.7 volts there. So we have 3.3 volts there. So therefore RB equals VRB divided by IB, which equals 3.3. Just trying to squeeze it on. A little tight for space. My apologies for that. Okay, equals 24.75. Equals 25K. Okay. All right. So anyway, that's one for you to look at. Here's another one. Okay, this one I did in Multisim. Okay. All right. And here we have the 10-volt supply. Okay, we're having a resistor in the collector of 680 ohms. Okay, and we have input switches here. Okay, so these are pull down resistors. We've already talked about those. Okay. All right, and we have 8K there. Okay, so here's all the form lists. See if you can. Here's the typical measure results on this simulation. All right, here's where was our target design. Okay, and see if you can get the same results. Right, so VRE. Right, so this is going to be your 10 volts minus your LED voltage of 1.8 minus VCE SAT of 1.5, right? So that gives us, right? This gives us here 6.7 volts, right? So the emitter resistor, right? On a test, I'm not always going to call it RC and RE. I'm going to start call it R1, R2, R3, R4. You need to know that's the emitter resistor because it's in the emitter line. Okay, so right, everything's not going to be always labeled like it was in the in class. Okay, because real schematics start R1, R2, R3. They don't, this is how it's done. Okay, so you solve for VRE. Right, and then the value of RE is the 6.7 divided by the 10 milliamps is 670 ohms. Right, the base current is the collector current divided by the assumed, which I would give you, the assumed beta DC of 100 gives you 0.1 milliamps or 100 microamps on the base. Right, VRB. So this is also RB. Right, it's the it's going to be the 10 volts, right, minus the LED voltage, right, minus VR2 minus VBE, right? So this line here is this line, just like that. And then the value of RB is very simply then VRB, which is 0.8, divided by the current, which is 8 kilo ohms. Okay, so I had the design parameters here, and I worked it out, then I built it, and seeing very, very, very similar results. I wanted 10 milliamps. Okay, I'm getting 10.4. I wanted, what do we have here? LED voltage of 1.8. Okay, well, what is it actually? Okay, well, look, we have 10 here, right? The voltage from this point to the ground is 1.7, right? Minus is 6.7. You could calculate the LED voltage, right? So this is really 10. Anyway, you can do it. It's okay, right? Right. Leave that for you for homework, right? So, yeah, I'm not quite sure. I'm not quite sure what that was. I'm gonna cross that out because I'm not quite sure why that's there. I'm not sure. Anyway, comments with this configuration, VCE, right? We're not going to fully saturate the transistor because we don't need to. Okay, but I've intentionally put it beyond 0. 0.7 volts, right? So because I don't want to saturate the transistor, right? So what this note here says is that, right, in order to have a 0. 0.7 volts VBE, we must be in the active area. Okay, so I haven't mentioned it before. When the transistor is forward bias is in the active area, the base, the collector to emitter junctions are reverse biased. The base to collector junctions are reverse biased. In the saturated region, the base to collector junction becomes forward biased, and I'm trying to avoid that. Okay, so that's why I used a 1.5 volt VCE. Okay, to keep it out of the saturation region, to make sure the transistor wasn't saturated. So anyway, so take these measured results and see what you can calculate from it, but you'll find it calculates very close to what our design specs were. For this case, I assumed VOL, which is going to be right here, was the ideal zero. If I gave you, 0.2, 0.3, remember it could be up to 0.5, right? It would just change the calculation very slightly. You'd have to account for that here. Okay, so anyway, you can play with that. So here we're using the PNP transistor to directly drive an LED, and the transistor is controlled by the logic gate output. And you can see then, in order to forward bias the transistor, right, the base has to be low, so the output of the gate has to be low to turn it on. So anyway, that's about it for today. Thanks for watching, and I'll catch you later. Bye.